reason drag is actually important. So you may remember this kind of slide that we had. I think this was way back in chapter 2, where we looked at the constant acceleration of objects. So this is kind of the culmination of Galileo's work, but ultimately the reason why Galileo was able to say that constant acceleration was because he was using the same object. A bowling ball of mass m and another bowling ball of mass capital M. They were both the same size, they had the same air resistance. So he wasn't really taking that into consideration. If we have different sized objects, or even if it were the same mass, if we have some big table like this falling versus a little giant missile or something that's the same mass as the table, but it's pointed, because it cuts through the air easier, it will have a different acceleration. So the main thing to realize here is drag is kind of like friction, in the sense that it definitely always acts in the opposite direction to where the motion is happening. So for instance, if the water bottle is going like the rocket that way, then the force of friction acts backwards. The force of drag has the same form. If the velocity vector is pointing that way, the force of drag acts in the opposite direction. It's something that slows down the motion. The motion is special though. It's not a surface and an object, so just two things rubbing against each other. It's moving through a fluid. And so the main way that we'll encounter this, a fluid is just, it could be a gas, it could be a liquid, everything that isn't a solid. So you're not moving through a solid substance. The main way, and this is what we're going to return to later on when we get to the end today, the real only way that we're going to actually use the force of drag is with skydiving and air resistance types of problems. So we're not going to use it a ton, but it is something that is a little bit interesting to talk about, especially because the world that we live in has very different laws of drag than microscopic organisms or something like that. Things get very weird when you get small and slow. So we already see that it acts in the opposite direction to the velocity. But the weird part about drag is that, unlike friction, it actually depends on the velocity itself, so the magnitude of the velocity. So even though it acts in the same direction, if I send my bottle like that, the force of friction acts backwards. But the force of friction, whether or not I send the bottle really quickly or really slowly, as long as it's kinetic friction, it only has one value. The coefficient of friction, mu k, and the normal force. The force of drag actually depends on the velocity itself. So the force of drag, we'll find out, if I send the water bottle through the air like that versus sending it through the air like that, has very different force of drag. It actually depends on the velocity. Very, very weird. So in terms of the types of things that differentiate drag from friction, it's basically the fact that there are two things that need to happen for an object to move through a fluid. One is that as I move this object through the air, there are a bunch of air molecules in the air that have to collide with this object and move out of the way. So this is very unlike friction. This is something we never really encountered with friction because we weren't working with a fluid that can move around. We were just working with molecules rubbing on other molecules. So this is one way that we can encounter drag. It's called inertial drag, or the inertial force of drag. And the idea here is that these air molecules have inertia. They are at rest and they want to stay at rest. And if you want them to move out of the way, you have to exert some force to get them to move out. Now, once they've moved out of the way, now they're along the side of your object. And so they're going to rub along the side of the object. That is much more similar to friction. And this is something called viscous forces. It's actually easiest to show a video of this before explaining the wording of it. So as this boat travels along the water, it is forming molecular bonds with the top layer of the water. All these water molecules at the top are getting attached to the boat, not completely attached, but in the same way that friction has that molecular bonding. As it goes along the water, these molecules are being attached to the top. And so they are being forced along the movement of that's the whole difference with drag and friction. The water molecules can actually move. And the way that drag arises is because they're not just free particles. It's not just empty air and one layer of water, every single layer of molecules underneath is also, there's some attractive force between those molecules. Otherwise, the water would just evaporate and go away. The water has attractive forces between it, just like any fluid, and those attractive fluids are basically going to mean, if I play the video again, you'll see what I'm talking about. The top layer of the water actually flowed quite quickly, whereas the bottom layer of the water barely moved at all. And so what's happening there is the molecular bonds between here is making that move slower, so they're being attracted, and being attracted until the boat comes to rest, because you can't move all the layers of water, basically is what's happening. So this is the idea of viscous drag. It's much more similar to kinetic friction in the sense that it involves things going along the side of the object, even though we're not, solid surface on solid surface. So in words, the way that this is working, the molecular bonds between the object that goes through the fluid and the fluid itself, they have some bonding, but then these air molecules are attached to other air molecules, and eventually that will act like friction and slow the object down. So that's why these two things are different. And thankfully, these are never really going to be important at the same time. It's actually, interestingly, a kind of active topic of research where you have both of them at play at once, but it turns out that oftentimes you either have a very big object that needs to move a lot of mass out of the way, or you have a very skinny object that encounters lots of friction along its sides. So oftentimes we really only have to work with one or the other of these. And so that is why the book does introduce this topic called the Reynolds number. The Reynolds number is basically just a way to compare these two forces. So the next slide we're going to talk about this Reynolds number, but it really is just a number that tells you whether or not you have a lot of inertial forces in your problem or a lot of viscous forces in your problem. That's really all it is. It's just a way to quantify that. So this is what this Reynolds number is. The book goes into more detail with this and actually gives you a formal definition of it, but without going too much into hydrodynamics, it's really not illuminating at all to derive it. It's pretty tricky to derive, so you can really just think about this as a ratio. And even still, I mean, there's a reason a lot of these equations on these slides aren't boxed. There's really only going to be one equation that I'm going to box for memory, because a lot of these are really just to talk about the difference between the types of drag. So the idea here is that when people say in like a research context, they'll say, I'm working with high Reynolds numbers. That means that in that situation, your inertial drag is more important than your viscous drag. Because if you say that my Reynolds number is high, if this is a big number, that means that number has to be way bigger than that number in order for this to be big. So that's what a high Reynolds number means. And that is basically the world that we live in. And we'll talk a lot more about that in a second. But basically this is a way that I kind of distinguish between these two things. A high Reynolds number where you're moving a lot of stuff out of the way, and a low Reynolds number, which would just mean your denominator is bigger. So if this is small, that means that has to be bigger than that. So in this case, this is more like where the viscous forces are more important. So I just like to think of my hand. If I push my hand through water, and I push it through like this, it has to move a bunch of stuff out of the way. So in that situation, the inertial forces would be more important, and that's more like a high Reynolds number. If I turn my hand like this, suddenly it doesn't have to move that much water out of the way, just the amount of my fingertips, and now there's a bunch of water molecules along the side of my hand that will slow me down. So that's how I like to try to remember this. Again, this concept of Reynolds number isn't crazy important. It's just an idea that either you're working with inertial forces, where you have to move a bunch of stuff out of the way, or you're moving with viscous forces, where you've got a bunch of stuff stuck to the side of your object. That's really all it means. So there are two ways to think about this high Reynolds number. There's either you can think about the kind of hand pushing through or slicing through the water, or you can just think about the size of the object. And this is where the book actually goes too far into this. The idea is that when you have different sized objects or things moving quicker, this is really the world that we live in. We are large objects, we're traveling at pretty high speeds, compared at least to like microbiology systems. So in biophysics, this is kind of the main way that people are working. Every time if we were to do hydrodynamics, we would be doing high Reynolds number hydrodynamics, basically the study of how fluids move around. Here, all of the physics is different. And what we're going to see, the main reason I do actually include the two types of drag force is just to see the difference between these two. Because it turns out that low Reynolds number physics is very weird and you can't swim in low Reynolds number. And the other kind of, I'll give you a little teaser here, if you were to stir your coffee in low Reynolds number, if you stirred it backwards, you could get your milk out. It's like a very weird world where you can't swim in the normal way that you think of, and time can kind of go in reverse because you can undo the stuff that you've done. So we'll talk about that in a second, but the main way that we'll use drag is in the high Reynolds number. And so this is one way where even this equation, even though I am boxing it, this is one that we really can't derive without a ton of work on like hydrodynamics, which is a whole other topic. So what we're going to do is just go through piece by piece and try to understand what all these variables mean. So this is something where we can talk about the force of drag as some object falls. So the first variable that is new in here is the drag coefficient, that CD variable. This is basically something that, it's like the spring constant, or the big capital G, or the coefficient of friction. It's just something that tells us how strong this particular brand of force is. And it has to do with how aerodynamic an object is. Without going too much into detail, it has to do with how easy it is for water or any fluid, as you displace it, how easy is it for that water to go back to its original spot, right? We're working where inertial forces are important. So how easy is it for the objects that are at rest, who want to stay at rest, to get back to the location that they want it to? That's basically what this drag coefficient is all about. And another variable, kind of skipping around a little bit, that's very related to this one, right? It's talking about the size of the objects, is A. And before I put a picture up here to kind of show you a few examples of this, in terms of the kind of taking my hand and pushing it through the water like that, or taking my hand and slicing through the water like that, this A, a cross-sectional area, is basically the area that's pushing through the fluid. So if I take my hand and I push through like that, then the cross-sectional area would be the entire surface area of my palm. It's everything that needs to push the molecules out of the way. If instead I slice the water like this with my hand, then the cross-sectional area is just the area of my fingertips as it goes through the water. So two very different situations, and we can have different cross-sectional areas for different shapes. So for instance, a way to think about this is if I were to drop a sphere through some substance, water, something maybe with a little bit more foam, something that actually, let's say I had a boiling hot sphere and I dropped it through styrofoam and it made a solid hole. The hole would be a circle. So that's what the cross-sectional area is. It's if you were to push through something, what shape would have been made by what you pushed through? So the surface area of my hand or the surface area of my fingertips. So that would be a cross-section of a circle. And then two very common things that come up are cylinders. And I have two ways. I can either push the object through the fluid like that. In this case, the cross-sectional area would just be a circle again. So this is where it's interesting to compare this drag coefficient and the aerodynamic aspect without going too much into a full study of that. This object has the same area as this one, right? The cross-section is just a circle. So the force of drag should just have the same form. It has the same cross-sectional area. That's where this drag coefficient comes in. It tells us about how aerodynamic the object is. If I have a sphere because it's rounded, it takes less time for the whatever fluid I'm going through. If it started here and I push a sphere through it, it's going to go in a very streamlined way around the object, back to its original spot. Whereas here, I'm going to hit a flat surface, be shot outwards, and then as I try to get back to my original spot, I'm going to hit the side of the cylinder. So it's going to make a very crazy path back to its original starting place. That's why the drag coefficient is different for those two objects. In a kind of a hand-wavy argument, that's what the hydrodynamics is all about. And for this one, this is basically just the last way that you can talk about a cylinder. Think about if I were to drop the cylinder through a fluid like this. The shape that it would kind of slice out is kind of try to squint your eyes and look at the water bottle and imagine it's not round. It's just a length and a width. So if I were to drop the cylinder through some kind of foam or something that shows me the shape, it would just be a cylinder. So the cross-sectional area with the cylinder is just going to be the area. Length times width. The length of a cylinder would be 2r, and the length. So that's a kind of a quick little explanation of where all those variables are coming from. The next variables are the speed. So this is where it differs from friction quite a bit. It actually depends on how quick the object is moving. If I throw my water bottle through the air really quickly, it has a bigger force of drag than if I just make it go slowly through the air. And the very last one is this object called rho. This is the density. So this is telling me how much stuff is in front of my object that it needs to move out of the way. So for us, this is basically going to be the air density. So I don't think we've ever talked about this object called density before. So density is basically how much mass is in a particular volume. So for instance, if I had a meter by a meter by a meter, I had a cubic meter of volume, how much mass could I put inside that? That would be my density. So it's mass divided by density. So if I know the units of mass are kilograms and volume is length times width times height, this would be meters cubed. So that's the units of density. It basically tells me how much stuff is in a particular region. And the main one that we're going to be working with, because we're going to talk about air resistance, that's really the only situation where we're going to actually solve things with drag. The density of air has a very specific number. We're going to define it at sea level. So that's how much atmospheric pressure. Basically, the atmosphere actually has pressure on us. So you can imagine up on the top of a mountain where there's less pressure, there's less tendency for molecules to be in any given volume. Same thing with temperature. If I ramp up the temperature, the air molecules are moving around quicker and they're less likely to be in a particular volume that I define. So lower pressure up on a mountain or higher temperature means my density is going to go lower. But this is just the density that we're going to use. It's the kind of standard density of air at atmospheric pressure and room temperature. Okay, so this is what we're going to actually use. We'll come back to this, but I do want to, respect the book's choice a little bit to talk about this stuff because there are some fun things that we can talk about, like mysteriously unstirring things and looking at swimming in these different contexts. So this equation is boxed. There's a reason why this next equation is not boxed. We're never going to use it. It really is just to show the difference between the two situations. When we have high Reynolds number and it's more important to move stuff out of the way, it turned out that the form depended on velocity squared. This, when it's more important how sticky the substance is, things sticking along the side of it, it turns out to depend on velocity. So that's kind of the B, it's just a coefficient that tells us about how sticky the fluid is, how big the object is, not super important. The main thing I wanted to point out is really just the difference between V and V squared, because that makes everything different. Just the fact that the forces that you experience are different, it means all the rules of physics are going to be very different in this case. It's not, it's not the as different as classical mechanics and quantum mechanics, but it is quite different. A lot of the forces that you experience here means that things are going to act very, very differently. And just to demystify it a little bit, you don't have to have a microscope to actually see some of this stuff. There are two ways that you can see examples of this that I can think of. I'm sure there are more examples. The two examples that I can think of are any time that you can see maybe light shining through the window and there's dust in the room or something. Any particles of air or particles or dust, anything that isn't air that you can see floating in the air, it's floating at such a slow rate because it's acting in a slow Reynolds number, or a low Reynolds number. The same thing would be true with honey or syrup. So anytime you're pouring something that has a really high viscosity, higher than the air that's around it, which is almost everything, you're going to encounter low Reynolds numbers. So these are two examples where you don't necessarily have to be working in a microbiology lab to see low Reynolds number stuff, but they're just some neat ways to think about this. So what I want to do now, before we get to actually utilizing that boxed equation we had on the last slide, was explain a little bit of those weird kind of mysteries I was talking about. Like, for instance, why you can't swim in low Reynolds number. So it may, the main reason here, that's a spoiler, we'll get back to that.
With their self-propelling bodies owe their thrust to inertial reaction of air or water to the motion of their propelling mechanisms.
So basically what that means is as you're swimming, the way that we swim is we are scooping water and then we're pushing on that water. And so just like the static friction allowing me to propel myself, or the rocket's thrust pushing down and then Newton's third law pushes me back, that's how we swim. But if you had honey to swim in, wouldn't work so well.
Well-defined wake. The body and tail of fish form another example, but here the wake is not so well-defined. Even a snake swims by moving its body so that each section of it is pushed forward by inertial reaction as the waves of bending move them obliquely in the water. All those we have seen have Reynolds numbers of order thousands or even millions.
High Reynolds number.
Microscopic creatures, which may have Reynolds numbers as low as 1/10,000, cannot derive any appreciable thrust from inertia. They rely on moving their bodies in such a way that they derive their thrust from viscous stresses. The tails of these bull spermatozoa move like those of tadpoles or snakes by sending waves of bending backwards so that each section moves obliquely in the fluid. Here, however, the viscous reaction to the motion pushes on the tails in the same way that it pushed on the obliquely falling rod. To illustrate the difference between inertial and viscous propulsion, I have constructed two models, both operated by the same source of power, a twisted elastic band.
So that would be something that is like swimming. It's trying to push water away, push water away, push water away.
Waving the rudder of a boat is so well known as a method of propulsion that yacht racing legislate against it. Putting this model in water shows us why. But when the model is put into syrup, it cannot move.
So it's basically the viscosity means that every time it's trying to move the object, it's just bringing the same molecules back and forth. So there's no way for that to work. The only way for it to work is to have a different situation. So you're not technically pushing anything out of the way. You're allowing the molecules to get stuck to one side and then just push them along until they get sent off the other side.
Because lateral resistance is greater than longitudinal, motion at right angles to the axis of the spiral.
This is basically how any microbiology organism works. They try to use something like that. They don't push the stuff out of the way, they allow it to get stuck to itself, and then they kind of wiggle through it. We definitely don't need to see that. And the next weird part about this is that if you were to stir your coffee in low Reynolds number, you could also unstir your coffee. So this is a very, very weird situation. They put food coloring in some kind of glycerin, something that's very sticky, basically. So the main, you may think like, oh, you put it in something sticky. Of course, you can just undo it. But look how insane these colors get. It looks like they've mixed. It's just apparently they have not, right? As they spin this, I can't even tell that they included 3 different colors in that. It just looks gray. And sure enough, as they start to go in the other direction, it will undo itself and look like time just moved backwards. So very weird. These are just 2 examples of the way that the laws of physics are quite different when you're working with low Reynolds numbers. There we can already see some of the colors coming back. And then magically, they have all separated again. I've always been baffled by this. It's insane. Basically, it's like, oh, time does move backwards. And that's, in reality, that is something that people talk about when they look at low Reynolds number. It's kind of a weird way to think about that the laws of physics don't actually work the same way that we would expect. Okay, so back to reality. This is the actual only equation that we're going to be working with in the drag context. So what we're going to do here is we are going to look at what happens as an object falls. You may have heard of this term, terminal velocity, before. Basically, as something falls, let's say it has 0 velocity up here. If it's under the influence of gravity, it is going to speed up, right? So if we know now that the force of drag depends on velocity, as the velocity of this object speeds up, the force of drag will speed up too. And that is going to just continue and continue and continue until the force of gravity acting downwards is exactly equal to the force of drag acting in the opposite direction. So that is when we're going to reach something called terminal velocity. As soon as the forces are balanced, there's no more acceleration, and then if there's no acceleration, you can't speed up anymore. So this is what we're seeing in this figure. This person jumping out of the airplane has no velocity initially. It just jumped out of the airplane. They do have an acceleration, and that's just the acceleration due to gravity. But as they start to speed up, right, they're accelerating, so they're going to gain velocity down here. As they gain more and more velocity, they're going to have an increased drag force. So the drag force, the velocity is going down, so drag force points up. And as they increase their speed, that's just going to get bigger and bigger and bigger. But notice what's happening to the acceleration now. Now we have a vector that points down and a vector that points up. So if we add those 2 together, it's going to be a smaller vector than what we started with. And it's just going to continue. The acceleration is going to get smaller and smaller until those 2 forces are identical, at which point we have no acceleration anymore. And what does no acceleration mean? That means the velocity is constant. So that's what the terminal velocity is. And because we have expressions now for each of these forces, the force of gravity is mg, and the force of drag is that slew of weird variables, we can set those 2 things equal to each other and solve for the terminal velocity. So what we're doing here is saying that we have no acceleration. Eventually, we've reached the point where the 2 forces are balancing and we don't have any acceleration anymore. So that just means we can set these 2 forces equal to each other. So writing out all those crazy variables up in the top, and then mg, the only thing we need to do to solve for the thing we're looking at, velocity, we need to multiply by 2, and then divide by the drag coefficient, the density of the air, and the cross-sectional area. Put that in the denominator, and then take the square root to get that v isolated by itself. So the ultimate thing that we're going to be using is this terminal velocity. And what we're going to do now is look at 2 examples for terminal velocity. We are going to have a person skydiving and a mouse skydiving. The mouse, you can exchange mouse with squirrel. That's what we're going to do in the video that I spoiled a little bit. The mass of the person, the mass of the squirrel or mouse, acceleration due to gravity. We're going to approximate their area as just a rectangle. So the skydiving person's like this, so we'll just measure their width and their length, and it's just an approximation. Obviously there are some holes in my rectangle. I'm not a flat rectangle entirely, so it's not exactly a perfect approximation, but that's what we're going to do. We're going to say their area is just a length and a width. So we're going to be given some masses. Let's say it's just an average human weight, 75 kilograms is roughly average. 2-gram mouse or several gram squirrel, either one is going to have a very similar terminal velocity. And because we're given a length and a width in this little figure, we can just make a smaller, it looks like the mouse is going to be a better approximation because they don't have very long arms. But It'll work for at least a little back of the envelope calculation. So if we multiply those two things together, we're just doing length and width to get the area for each case. And because we were using a rectangle for the area, what should we use for the drag coefficient? Remember that there was a rectangle before when we were looking at all those drag coefficients. This is just a cylinder. So the area, that is the width, that is the length. So we already have length and width. So we're using a rectangle. That means the object that we're kind of modeling this human and mouse after is a cylinder. So we should use 1.1 as our drag coefficient. And the very last variable is just to say that we're falling through the air. So the density of the air is 1.2 kilograms meters cubed. So plugging all these things in, we see that the terminal velocity of a skydiver, and that's actually a low estimate. If we were to actually make this area a little bit better, it would actually be higher than this. But even still, that's a low estimate. And if we look at that in miles per hour, it's 90 miles an hour. So just, yeah, I've never skydived, but it's just insane to think about like sticking your head out of I mean, you shouldn't be driving at 90 miles an hour anyway, but if you did, that's a lot. A mouse is way, way, way lower than that. Or a squirrel, anything, it's way lower than that. And what I want to talk about before we end is that velocity is the terminal velocity of these mice or squirrels. Let's just quickly try to figure out how far a mouse or squirrel would need to fall to reach that velocity. Because it's actually not much. So how are we going to do this? Let's say the squirrel or mouse, they jump off of a building. So initially they don't have any acceleration, or they don't have any velocity. They're just falling through the air, so they've got negative 9.8 meters per second. And I'm going to try to figure out how far they need to fall in order to reach their terminal velocity. So if we plug all these things in, I don't have any time here, so I'm going to use my no time kinematic equation. It turns out that the mouse or squirrel would only need to fall about 7 meters before they reach this terminal velocity. So just for some architectural perspective, one story in a building is about 3 to 4 meters-ish. So that distance that the mouse or squirrel fell is just a 2-story building. And that velocity is so small, that's roughly like 20 miles an hour, something like that. And because especially squirrels have such good like shock absorbing legs, same thing with a cat. A cat's another example of this. They have very good shock absorbers, so they will not be injured by a 20 mile an hour collision. So that means if the animal can survive, a mouse or a cat or a squirrel, if they can survive a fall from a 2-story building, they can survive a fall from a 200-story building, because their velocity will be exactly the same when they hit the ground. As soon as they fall that distance, they're not moving any quicker. So there are a bunch of video. I would highly recommend going on YouTube and looking at like animals falling from, especially squirrels. They're really good at it. There is this video, which is hilarious in and of itself, but the only reason I chose this video was because it does include one of those videos that I'm talking about, where